I'll give it another minute. Okay, it's 1:30. Hello, everyone. So the first Mobius assignment, real Mobius assignment, will go live on midnight. So Casey, I just saw your comment. Can we discuss electrostatic potential? It's on the lab this week. Um, I so electrostatic potential is basically talking about dipoles. So we've already kind of briefly covered that, and so lab is covering some stuff that's a little bit outside of the core of the course. And the idea is that we have both the course material and the lab material, and they are running in parallel, but they're not completely overlapping. So I'm just going to continue with the lecture component for the course. So the live, sorry, I'm trying to get my brain in gear, and it's not in gear. The first Mobius assignment goes live today at midnight. I'm going to repost the practice one. You can't do it again if you've already done it. I'm going to modify and call it something else. So I guess you actually can do it again, but it doesn't count for anything. And so if you want to practice submitting things, or you accidentally submitted things, or you didn't get a chance to practice, and you want to go practice and try working it through, I'm going to post that this afternoon after class. The other thing I'm going to post today, hopefully today, is a couple of practice assignments on some of the stuff we've already covered. So you can do them over reading week. You can start doing them earlier. They are just pen and paper assignments. I post the answer key. I post the questions. I post the answer key online. You can use those as you see fit. And they're just practice to sort of see what kind of questions I ask. The Mobius assignment that's going live tonight at midnight is compulsory. The Mobius assignment that you can practice is not at all compulsory. And my assignments are not compulsory. You can do them or not do them. I don't care. I recommend you do them. Like, I put them together for a reason, but you're in charge of your own education. So where we left off last class is we were talking about the 1,3 diaxial interactions. Kind of ad nauseum, actually. I'm really bored of them. I'm just gonna pull my thingy over. Yes, the real Mobius assignment starts at midnight tonight. It goes till midnight Friday night. So you have 48 hours. You have to do it. If you choose not to do it, you get a 0, which is your choice. You can choose to take a 0, I guess. But yes, it is. This one is mandatory. And I'll post an announcement on Blackboard for the, however many people aren't here. Half the class that isn't here. You should be able to leave the assignment and get back to it later. Yeah. You just can't go back. Once you submit a question, you've submitted the question. So same rules as last time. Okay. It's weird. Okay, now it's my computer screen that's blowing on my face. Okay, I can't win. So we have two different types of disubstituted cyclohexanes. So if we were talking about cis and trans, we were kind of laying off at this idea. We were talking about these A values. And so if you have a 1,3 dimethyl cyclohexane, you can have cis 1,3 or you can have trans 1,3. The cis 1,3, just because the way these chairs are always done, you got an axial. I'm going to turn my camera off so the picture's bigger if I'm not needing it in the moment. So in the cis 1,3, you have the two groups axial to each other because that's the way that works, or they can be equatorial to each other. And of course, the diaxial, as we were discussing, is really, really bad. And diequatorial is pretty stable and pretty good. In the trans 1,3, well, one of them's axial, and if the other one was axial up, so up and up, The hydrogens are in the down position, so they're cis because both the carbons are on the up positions. If this was in the up position, it would be cis, so it has to be down. So this methyl group is up relative to this hydrogen. This hydrogen is up relative to that methyl group. So the hydrogen and methyl group are on the same side of the cyclohexane. This hydrogen and that methyl group are on the bottom side of the cyclohexane, not on the same side. So if one's axial, the other one's equatorial in this case. And you can ring flip, and you swap them. So the red one becomes equatorial, and this green one over here becomes axial. Those are, of course, the same energy total in those conformations because it's the same molecule. So the cis isomer is more stable than a trans, and that's because the cis has a conformation where they both can be equatorial, whereas the trans doesn't have that available to it. So this is better. 2 equatorials is better than 1 equatorial and 1 axial. But by how much? And the way we can measure that is by basically looking at the differences in the A values. So if I scroll back up, we're going to just take a look, and we have this methyl here. That's the difference between having an axial and having an equatorial. And it's 7.6 kilojoules per mole. Well, surprisingly, this is awfully close. I think it is more stable by 7.5 kilojoules per mole. And that's essentially the difference between having this equatorial and having that axial. And it's basically pulling that number off the A value table. And A values are additive. They're not exactly additive. You see there is a slight distortion because there is another methyl group, so that does distort the value a little bit from the ideal 7.6, but not by much. Essentially, they're the same. And so what you can do is you can add up all the A values and subtract A from one from the other to get the right thing. So what I mean by that is, let's go back up to this one so we can see this. So let's say we had a chair, and it had fluorine's on here. Good. It had a fluorine, and it had a cyanide, and it had a, I don't know, let's stick a methyl group there, and an ethyl group there. And so we ring flip the chair. And when you ring flip a chair, so one way you can do it is, we here, drawing the other chair, and I ring flipped it. And what I'm essentially doing, I number my carbons, is I'm slightly changing my perspective as well. So carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. What's important is that 1 through 6 is clockwise on the left-hand structure. 1 through 6 is clockwise on the right-hand structure. You need to make sure that's still the case. And I basically flipped the chair and changed the perspective a little bit. I've changed my angle of looking at by a tiny amount. And so the fluorine was axial and up on carbon 1. There was a hydrogen that is equatorial and down. So on carbon 1 in the chair flipped, note I'm drawing the new bond parallel to the carbon 2,3 bond. It should be, because that's the one bond in the chair that isn't connected to carbon 1. So this should be parallel to that. And it's equatorial, and it's still up, because there's going to be an axial down hydrogen at carbon 1. At carbon 3, I had an equatorial down cyanide because there's an axial up hydrogen there. And so now that's going to be an axial down cyanide. On carbon 5, I had an equatorial down methyl group because there is a hydrogen that's vertical and axial. And so now it's going to be axial down methyl. And on carbon 6, I had an axial down ethyl. And now it's going to be equatorial down. So what I've done is all the axials have become equatorials. All the equatorials have become axials. We're still going clockwise. Just flip the chair. I haven't turned it upside down. I've just inverted the chair between 2 different chair forms. And what that means is all my axials become equatorial and all my equatorials become axial. And so if I'm looking at this, I'm trying to figure out how much more stable is one of these than the other and which one's more stable. What I can do is basically sum up all the A values. So I'm going to call this one A. I'm going to call this one B. So B has the fluorine going equatorial instead of axial. So B has 0.8 kilojoules per mole in its ballpark because it is 0.8 kilojoules per mole more stable because of that fluorine. Now A has the cyanide axial, whereas equatorial, whereas it's axial in B. So look for cyanide. There it is, 0.8. A is 0.8 better. So that's actually kind of a wash. Those two are going to cancel each other out. Okay, so now we get down to this methyl group. So the methyl group is equatorial in A, so it's beneficial in A. There's methyl, it's 7.6. And then we have the ethyl group, and the ethyl group is beneficial in B, and there's ethyl, and it's 7.9. We can do the math. And B wins by 0.3. And you add all those up. So that's this one more stable by about 0.3. It's going to be off by a little bit, but more or less, we can add up all these A values. And we get to this value here where we can get sort of the idea of how much more stable this one is. I'm going to erase these highlights on here so they're not gumming up the answer, the posted marked up thing. So you can add these up to figure out how much more stable something's going to be. Okay. And so you can do that all the time. So again, what you've got here is you see this in action where you have these two molecules. And we can see from the equilibrium arrow that having the bigger group equatorial is better than having the smaller group equatorial. And that's exactly what we think, because again, it's stuff banging into each other. So somebody's saying, why are you comparing the values of the methyl with the ethyl? It's not so much that I'm comparing the methyl and the ethyl, it's that I'm comparing everything. And like each of them have two benefiting them. So each of them, so A is 0.8 kilojoules per mole more stable in terms of the cyanide. B is 0.8 kilojoules per mole in terms of the fluoride because of that value there. The ethyl group is equatorial in B, and so B is 7.9 more stable because of the ethyl group, whereas A, the methyl group, is equatorial, so it's 7.6 more stable. So it's not that I'm comparing 0.8, 0.8, and 7.6 and 7.9. It's that these two favor A, these two favor B. Add them all up. This is 0.3 more. So this is 0.3 more stable than that one. Because again, these are energies. These are which one is more stable. These are all values are all negative is basically it. So I could have stuck negative values in front of these because when I said this is more stable, you're more stable because you're 0.8 more negative. So Simmer said, wouldn't A be more stable since it has less energy? It's actually minus 0.8, minus 0.8, minus 7.6, minus 7.9. So this value is minus 0.3. So B is more stable by minus 0.3. I'm comparing the axial to the equatorial, Amanda. So I'm looking, where is it equatorial? And I'm giving it the value there. Okay. Now, we get cases with really, really bulky groups. And this is the one exception where this is the only exception of this we're going to see in the course where tert-butyl is always equatorial. No matter what else is going on, it will never be axial because it's just so much bigger. And I think if you remember going back, there's like 23 point something. So you'd probably come to that anyways with the math. But tert-butyl is always, 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 always equatorial. Then just something I do want to highlight, we're not really going to spend much time talking about these in this class. You're going to see some examples. We're going to have to worry about the conformations too much. You can have bicyclic molecules, so things where you have two cycles connecting together. And actually most drugs are this form because it really positions things in the right shape and gets everything in the right spot relative to one another and not flopping around like they're on some sort of chain. So you get these called fused bicyclics, where you basically attach two rings together. You have bridged bicyclics, where you get two rings because they kind of bridge each other. It's kind of when you have a fused system, but instead of being next to each other, they're kind of one carbon away. So you kind of have a 5-membered ring over here, and you have another 5-membered ring over on this side of this thing. And then we have stereocyclic systems, where the two rings fuse together at a single carbon. One atom shouldn't be carbon. It could be nitrogen as well. Adjacent atoms. Not adjacent atoms. So the 4-4, so this is what this is called as a nonane, because it's got, so this is a stupid name for these molecules. So it says, look, there are 9 carbon atoms here. That's true. And from that spirocenter, one is a 4-membered ring and one is a 4-membered ring. So I could have a spiro 5-3 nonane where one was a 6-membered ring and one was a 4-membered ring. But this is the 4-4. This is stupid nomenclature. You don't need to know it for this class. This one's basically saying it's a 2-2-1 heptane because 1-2, 1-2, 1. So those are the number of atoms on the different cycles there. The one we are going to see a bit is decalin. Decalin is a fused 2 6-membered rings. And I think the next slide should be about decalin. Or it's not. It's not. Okay, so I'm going to go just draw that. This is hard to draw. So cis-decalin has the 2 hydrogens on the same side of the fusion junction. And you got 2 chairs, one kind of at 90 degrees to the other. Notice I'm trying to keep this equatorial right and that axial right. And then once I've done that, I've got my 3 sets of parallel lines, and I just now need to finish the other chair. Transdecalin is a whole lot easier to draw. You just draw 2 chairs next to each other. And what's interesting about this is this guy cannot ring flip. This guy can ring flip. And if you don't believe me, build a model. And this is a good example of time to play with your model kit. So if you need, and you probably do want to practice some of these things, these are on the previous lecture with the recommended questions. So in this 2-part lecture over the 2 days, we talked about cycloalkanes are strained due to angular torsional strain if they're not 6-membered ring. And depending on the size of the ring, we can increase those 2 components. And together they cause ring strain. Kind of ring strain is the sum total of angle strain and torsional strain as sort of 2 different terms. Cyclohexane exists in a chair conformation that can interconvert via a boat conformation. Big groups like equatorial, all groups like equatorial. Everything that's not a hydrogen wants to be equatorial, but you want to get your biggest groups equatorial. And bicyclic alkanes exist. So we can do maybe a couple of examples here. So if I said draw the structure of cis 1-bromo 2-methyl cyclohexane. So just take a second. bonus marks if you draw it as a chair. I would ask you to draw this as a chair, but that's not what I put on the slide. Okay. So if we're not going to draw as a chair, if we're just going to draw as a hexagon, because why make your life harder if they didn't ask you to do something? It says cis 1-bromo 2-methyl. So I want the bromo and the methyl on the same side of the chair or the ring. So I'm going to put my bromine coming out towards me. And I'm going to put my methyl group coming out towards me. That's 1. That's 2. That's a cyclohexane. There's a bromine. There's a methyl. We're good. If you want to draw this as a chair, draw that. Or you could flip the chair. And this is a trick to flipping chairs. Instead of flipping the chairs and driving yourself flipping nuts, what you can do is slide every atom 1 atom over clockwise. That's the flip chair. I've made all my axials equatorial and all my equatorials axial, and I've kept going clockwise from methyl to bromide. And I haven't needed to redraw my chair. I don't even need to learn how to draw the other type of chair. I only need to draw the one type of chair, like pointing the one way. And I save myself a lot of trouble. Okay. So the second question here says, would combustion of cis 1,2-dimethyl cyclopropane or trans 1,2-dimethyl cyclopropane release more energy? So take a second to draw those out and think about your answer. So our two options are that or that. So let's think about what the question is asking. It's saying when you burn these two, which one releases more energy? So it's basically saying which of these two has more energy in its bonds, which is another way of saying which of these two is less stable. So what this question is actually saying is cis 1,2-dimethyl cyclopropane or trans 1,2-dimethyl cyclopropane less stable? We got 1 vote for cis is less stable. Okay. In a class of 330 students, we have 4 votes, which is great. 6 votes. Okay, they're starting to come in. Any dissenting opinions? Doesn't look like it. Y'all are group thinking, but you're all right too, so it's all good. So hopefully what you're thinking is, look, I'm thinking about strain. And if I remember what the cyclopropane looks like, and I draw my carbons, and then I've got a hydrogen coming out and a hydrogen going down, a hydrogen going out. This is just standard cyclopropane. And if I remember right, everything is eclipsed. Everything is eclipsing everything else. And you can build a model and play with that. You're always welcome to build as many models as you want. So if you don't see why all these people are right, the trans has the 2 methyl groups not eclipsing each other. I erased the hydrogens and they've just turned into CH3s because the magic of chemistry. So they're not eclipsing each other, which is good. So you don't have the big electron clouds of the 2 methyl groups whacking into one another. Whereas the cis does have the big electron clouds of the two methyl groups basically whacking into one another, and they can't get away. They can't rotate out of conformation. So the cis releases far more energy because it's less stable. So what we're doing here is we're sort of walking through what does this mean to release combustion energy, and it talks about stability. Okay. I think that sums that. Oh god, there's more. How many axial hydrogen atoms are there in the more stable conformation of cis 1ethyl 3 methyl cyclohexane? So give everyone a few minutes. This is good. It breaks up me nattering at you. So depending how you want to think about this, and depending how you want to solve these problems and how familiar you are with chairs already, probably not that familiar, you might want to start by drawing this thing out as a cyclohexane, like as a hexagon, just to make sure that you get all the pieces together. So cis 1ethyl 3 methyl. 1ethyl, 3 methyl, and they're cis, so they're both coming out of the plane towards me. It is equally correct to draw them both going into the plane away from you. It is not correct to draw one coming out and one going in. It is also not correct to not indicate some sort of stereochemistry. We're going to talk about stereochemistry in the next lecture. So let's convert that into a chair. And so one option, sorry, I've switched from clockwise to counterclockwise there, so that's not good of me, is to have the ethyl and the methyl cis and both axial. And that sucks. So we're going to use my little swing it over one carbon. Or you can have them both equatorial, which is much better. So this is more stable. So the question it asks, how many axial hydrogen atoms are there? Well, there's 6 because every single one of these carbons has an axial hydrogen atom in this more stable conformation. So the answer there is 6. In a less stable one, the answer is 4. Okay. Yes, please do. Sorry, you're seeing the sausage getting made in real time. Okay. Where's my mouse? So, yeah, everything will be uploaded before reading week. I'm sorry. I think for whatever reason I didn't upload at the end of last class. I'll make sure those are uploaded. I'll make sure that's uploaded too. Yeah, absolutely. I think one of the lectures had no annotations, so there was no reason to upload it. So chapter 4, because my pen broke and so I wasn't using it. We're going to talk about some things about stereochemistry. So again, what is it's a type of stereoisomers. Stereochemistry is the study of the molecular arrangement of atoms in space on a molecule. And stereoisomers are a form of isomer. We're going to be talking about stereoisomers. So last, I can't remember when, sometime in a distant past of September, we talked about constitutional isomers. And those are isomers of a molecule. They have the same molecular formula, but they differ in the bonding sequence. So different atoms are attached to different other atoms. Stereoisomers have the same bonding sequence but differ in the orientation of atoms in space. And so we briefly talked about this with double bonds, where you can have something like fumaric acid and maleic acid. Everything is attached to the same atom, but one is a cis double bond, or it's on the same side, so it's a Z double bond, and the other one is on the opposite side, and so it's an E double bond, or a trans double bond. And these are different molecules. They have really different melting points, like, we're not talking like a few degrees here, we're talking like 150 degrees. That's considerable. This one you can eat, and you need to, and it's actually used as a really expensive cancer drug under a brand name, and I can't remember what the brand name is right now, but it's just fumaric acid, and it is insane that it's expensive. And the other one, maleic acid, is really, really toxic, but far more soluble and does not have the same impact on things. So today we're going to talk about chirality. Has anyone been exposed to chirality before? Okay, a few people. Some. Okay, I'm getting some no's. Okay, so there's some no's and some yeses, so it's a whole huge metric ton of mess. Okay, so we're going to define chirality. We're going to determine whether stuff is chiral or not, and then we're going to determine whether molecules are chiral. What is chirality? So a chiral object has a mirror image that is different from the original object. That is the definition. You have a non-superimposable mirror image. So something is chiral if it is non-superimposable on its mirror image. So for example, in this picture here, I've got a chair. There is a chair in the mirror. Mirror chair and real chair, if mirror chair was real, and like it was like in an alternate universe, they would be identical. Because the mirror image and the real thing are superimposable, right? I could move the real chair through the mirror, and I could put it right on top of the chair, and everything would be the same. So a chair, or this model of chair, you might have like some sort of fancy, French chair thing, which is chiral, but a standard Scandinavian simple chair is superimposable and is achiral. So let's think about some things. I'm going to turn my camera on, and we'll see how well. Where's my mouse? There it is. Oops, but that's the wrong screen. We'll see how well this whole YouTube thing works. I guess we'll find out. Proof's in the pudding. So I got my hand. So the mirror image of my hand is my other hand, right? You can think about it. There's a mirror down the middle here, and what I would see from this hand is my other hand, more or less. Like I'm wearing a ring here, so I guess that's different. Okay, now it's my hand. Just hairs are different and stuff, but I can't do anything about that. So complete mirror images of each other, but they're non-superimposable. So if I take this hand and I stick it palm forward towards you, and I'm trying to superimpose my two palms on one another, my thumbs are in the wrong place, which is very convenient being a human being, because achiral hands would be irritating because your thumbs would be stupid. But my thumbs cannot superimpose. And if I try and superimpose my thumbs, suddenly my backs of my hands and my palms of my hands aren't superimposing. So my hand is chiral. It is I have a non-superimposable mirror image on that. And if I click a button, yay, I'm right. Okay, which is handy. So your nose, if you're a kitten, and let's say you had a perfect nose, and you did a mirror image right down the middle of your nose, and your nose was perfect. None of our noses are perfect. It would be superimposable. The left nostril, you take the mirror image of that, you can superimpose it directly on your right nostril. Now, of course, this particular kitten seems to have, a little bit of a thingy over here. So their nose would actually not be superimposable because the left nostril is not the same as the right nostril. But in a perfect world, it is true. Chiral objects may or may not be asymmetrical. It depends what you mean by asymmetric. So again, a glove is chiral because a glove is your hand. That's kind of cheating, actually, isn't it? And if we think about an ice cream scoop, is that chiral? If we have a mirror image and I have an ice cream scoop next to it, and this isn't one of them fancy ice cream scoops for right-handed or left-handed people. This is your bargain basement dollar store ice cream scoop. There's no difference in the left side and the right side of the ice cream scoop. So the mirror image of the ice cream scoop is the same as the ice cream scoop. And if we think about a screw, a corkscrew, corkscrews are chiral because screws have handedness. You have either left-handed screws or right-handed screws. Because, you know, lefty loosey, righty tighty, or when it gets really confusing when they have it threaded the other way. That is chirality. They are different. They are not achiral. A nail is achiral because it's got now this helical bullshit going on. Now, that's great. None of those are molecules. So if we talk about molecules, what we want to be looking at is a molecule chiral? I'm going to now minimize my video because I'm no longer showing my hand. Oops, wrong place. So is a molecule chiral? So if we look at this kind of molecule here, let's just remember what everything means. This is how you'd best draw a tetrahedra if you haven't practiced drawing them. You've got two bonds that are in the plane about 109.5 degrees apart. I'm not getting out a protractor. 120 is fine. But not 90 isn't good and 180 is not good, so something in between. And then you have a bond coming out towards you and a bond going back and away from you. And there's the big spot over here that's not like the oblique angle outside of the smaller angle between these guys. So that's what that means. Now I can draw a mirror image of it. So I drop a mirror down here and I put every atom equidistant from its partner on the other side of the mirror. So the bromines are both in the plane going back and away from me. The chlorines are both up. The hydrogens are coming out towards me, and the methyl group is going away from the mirror. Yeah, we're going to get into enantiomers. So is this molecule, so I'm asking, is this molecule chiral? And so what I'm saying is, are these mirror images superimposable? Okay. Now I'm not quite sure what's going to happen if I click my mouse. I will find out. Okay, well the answer is they are chiral. And the reason is because they're not superimposable. So what I'm going to do to show this, for those of you who haven't seen this before, is we're going to have an axis that is right down the middle of the plane of the paper, and I'm going to do a 180-degree rotation of this guy. So when I do that, and I'm going to use my rotation arrow, it's got a little loopy thingy in it. This is not an official arrow. I think I'm probably the only person who uses them, but it's really good because it allows you to quickly show that you're rotating something. The methyl group is now going to be directly into the plate. So yay, I can compare. My chloride is going to be coming out that way. Again, I've rotated 180 degrees around this thing. Imagine flipping it. I'm still going to have a down wedge and an up wedge here. Except now, when I rotate 180 degrees, the bromide is going to be coming out of the plane towards me. And the hydrogen is going to go back into the plane away from me. So your Mobius has some interactive things where you can play around with the stereochemistry, which is kind of fun. I really recommend you get out a model kit for this. And I'm at home and I do not have a model kit on me, which was really not my brightest moment. This would have been useful. Okay. I might have to run in and get one for Friday. So in this case, when I try and superimpose it, so I can superimpose the chlorine and the methyl group onto the left-hand molecule there, but my bromine wants to be on top of the hydrogen, my hydrogen wants to be on top of the bromine. They're non-superimposable mirror images. So these are mirror images of each other. They are not superimposable. This molecule is chiral. We call a pair, oops, now I'm just flipping randomly through things. We call a pair of chiral the mirror images of a chiral molecule are enantiomers. So enantiomers are mirror image isomers. Compounds are non-superimposable mirror images. And you have enantiomers when you have a chiral molecule. I'm going to come back to this definition in a class or two, or maybe at the end of this lecture, which isn't going to be today. Because it's not, I don't love this definition. It's an operational definition, but it doesn't actually cover everything. So we can ask, is this molecule chiral? So we can draw the mirror image like this. We're going to do that same rotation that we just did, because we're going to see, can we superimpose this? And when we do that, we get that as a rotated, this 180-degree rotation. And the temptation is to go, haha, this is not a superimposable molecule because this is not the same as that. I gotcha, it's chiral, and you'd be wrong. Why are you wrong? Well, you're wrong because you haven't explored all the things you can do to rotate this. So this was that same rotation along that axis that we just saw. Yes, it is. This is a sideways Scandinavian chair. We can really play into that pun if we start talking about like cyclohexanes. I was going to go there, but you kind of broke it. Thanks, Bennett. Okay. What we can do now is draw a new axis. And we're going to change color to draw this new axis. I'm going to draw the axis right along that carbon-carbon bond there. And we're going to rotate by 60 degrees. And when we do that rotation, that methyl group stays in exactly the same place. But I'm just going to label these chlorine number 1 and chlorine number 2. Chlorine number 1 drifts down to where the hydrogen was. The hydrogen comes out to where chlorine number 2 was. And now chlorine number 2 has rotated up to where chlorine number 1 was. Hopefully everyone can follow that. I'm spinning. I don't have a camera on. I'm basically spinning this guy around. So we're keeping that methyl group steady, and we can spin the other guys all the way around. That's what we're doing. Whee! And so in that case, now, this, of course, is the same. And the reason it's the same is because we cheated. So let's pretend that we could label our chlorines. We can't. All chlorines are the same because they're chlorine. But what we managed to do is when we took, I got my chlorines mixed up. There we go. When I took the mirror image of this guy, there's chlorine 1, there's chlorine 2. I do the rotation around 180 degrees around here. Okay, chlorine 1's out here. Chlorine 2 is now coming out towards me. Great. Then I spin, and now chlorine 2 is up where chlorine 1 was. Chlorine 1 is where the hydrogen was, and the hydrogen is where the chlorine 2 was. And now when I take this, I can superimpose this on that. What I'm doing is I'm putting chlorine 2 on top of chlorine 1 and chlorine 1 on top of chlorine 2. And it's because all chlorines are the same. And so these are superimposable mirror images. We couldn't have done this with the previous example because the atoms were all different. So if we had here, we had a methyl group, a hydrogen, a bromine, and a chlorine. Those were all different. So I couldn't, there's no way I could have spun those to be separate. But here I had this benefit of having two of my atoms being the same. So this is an achiral molecule because the mirror images are superimposable. And the mirror images are superimposable because two of the atoms are the same. So what makes a molecule chiral? I can't say that I without laughing. I really like Futurama. If you haven't watched Futurama, you probably should. Anyways, there's a line in there, what makes a man neutral? And I feel the same way about this. It really isn't very funny if you haven't seen it. Okay. What you need is you need an asymmetric carbon atom. Now, you might have been taught that this is called a chiral carbon. It is not. That is a horrible term, and it will be scrubbed from the record books. Atoms are not chiral. Molecules are chiral. I am going to make that mistake because I was taught wrong. So you need an asymmetric carbon atom. What the hell does that mean? It means a carbon bonded to 4 different groups. It is a center of chirality. Sometimes gets called that. I still hate this. This has been a thing we don't do since 1970. It is still in almost all the high school textbooks. So if you've come across this term, this is what we're talking about. We aren't going to use that word. We are going to call this a stereocenter. It is a center where there is stereochemistry. So molecules are chiral, atoms are not chiral. Mohammed, you're mostly right except when you're really wrong. So Mohammed said every tetrahedral structure with 2 of the same groups is achiral. If they're all different, it's chiral. That's not completely true. It's mostly true. Except when it isn't. But you need a molecule that has this. Without this, it cannot be chiral. If it does this, it still might be achiral. But you cannot have a chiral molecule without a stereocenter. And so that is a carbon that is drawn to 4 different groups, as Mohammed has said. So asymmetric versus non-asymmetric, an asymmetric carbon or a stereocenter has 4 different substituents. Can be anything, as long as they're different. Carbons with 3 different substituents are not asymmetric. And we just saw the example of that, where you have the mirror images drawn like this. I do a 180-degree rotation around this guy, and boom, suddenly they're superimposable. And again, we've done this cheating thing where if we had done 3A and 3B, and we could keep them separate, suddenly we're putting 3B on top of 3A and 3A on top of 3B. And so we'd be cheating. But you're allowed to cheat because they all look the same to nature. So rotation, so Paige says, so for chiral, it's not just one mirror image, it's actually every change in rotation. Yeah. Molecule, chiral, like if a molecule is chiral to the other one, it is never superimposable. No matter how much you rotate it, it's never superimposable. Whereas if a molecule is achiral, it's superimposable and you're going to have to probably do some rotations. And it's because things can rotate as much as they want, right? Like my hand is my hand, whether it's upside down or upside or right side up or left or right or anything, it's still my hand. So yeah, you can rotate that and it's still my hand. You're not changing anything about my hand. So in general, if a compound has no asymmetric carbons or stereocenters, it is an achiral molecule. If there's only one asymmetric carbon, it is chiral. So that's where Mohammed's definition works. If there's only one asymmetric carbon, it is chiral. If there is more than one asymmetric carbon, the molecule may or may not be chiral. Isn't that wonderful? So if we think about a guy like this is a cis dichlorocyclopentane. It is pretty clear that those are superimposable. Yes, slide it over. That one's doable. This one, looking at it, thinking about it. If you slide it over, it's not chiral. If you flip it, slide it over, it's not superimposable. If you flip it, it's not superimposable. Like if I just do a 180-degree rotation right around the axis of the plane, this chlorine will be down, this chlorine will be up. I don't think these are superimposable. And because of that, it is chiral. They are not superimposable. So one way of measuring this kind of thing is if a molecule is an internal mirror of symmetry, it cannot be chiral. So this example here is one of these examples where that's a stereocenter. That carbon is attached to 4 different things. That's a stereocenter. That carbon is attached to 4 different things. This molecule has 2 asymmetric carbons in it. It has 2 stereocenters, but it's achiral because those stereocenters are symmetrically equivalent. You can superimpose one on the other. And this baby has a plane of symmetry. You could stick a mirror down the middle of the molecule and you would see both same things on both sides of the mirror. This guy does not have a plane of symmetry internally. You can't stick a mirror anywhere on this molecule and see the same thing on both sides of the mirror. We're at 220. So I think the last thing I'm going to do is just leave this comment here. But the converse isn't true. A molecule without a mirror plane isn't necessarily chiral. This molecule does not have a mirror plane. Here is its mirror image. These are superimposable. If you don't see that immediately, you got to do a couple rotations, and you got to do them in your mind. And if you don't see that immediately, please get out your model kit and see it with a model kit. This portion of the course is going to play into reactivity later in the course when we start talking about that. It's important. This portion of the course is also what you need your model kit for, because you are now needing to think in 3D, and we are drawing them in 2D. And drawing stuff in 2D with ramifications in 3D is really tricky, especially when the person drawing is me and I'm a really shitty drawer. Though it'd be kind of awful no matter who is drawing these. So please, if you don't have your model kit with you, you shouldn't leave it at your office at work like I did. And it's not a bad thing to have it around during these lectures or to practice after lectures, trying to build these models and convincing yourself of superimposable versus non-superimposable systems. Okay, so just a reminder, the Mobius assignment goes live at midnight. The Mobius assignment covers everything in the course up to Monday's lecture. So it doesn't sort of like cycloalkane kind of stuff. It doesn't cover the stereoisomer stuff that we're covering today. Okay, have fun, good luck, enjoy your well, no, I guess we see each other one more day before reading week, but take it easy. I'm looking forward to reading week. I'm sure you are too. Or no, reading week is the week after. I have no idea what the hell's going on. I will see you guys all later. Take it easy. And I'm going to stop recording when I figure out how to do that.